Good morning. Abhinay, you are the host now. Moment come into co-host and same way with the faculties also.
Okay, sir.
Okay. Good morning, ma'am.
Good morning. Okay, are you able to see my screen?
Yes, ma'am. Yes, ma'am.
It is in full screen, isn't it?
Yes, yes, yes. It is in full screen mode only, ma'am.
Okay. Okay. Thank you so much.
Thank you. Thank you.
Good morning, Ligy madam. I am George here. Madam, I am audible, no?
Yes, you are audible.
Okay, okay. Yes.
You can hear me, isn't it?
Yeah, yes. It's clear. So, how are things at IIT campus, madam? The COVID situation there?
It is fine. Okay.
Okay.
Earlier some few cases were there. Now it is reduced significantly.
Okay. I think all scholars are there, and even MTech students are also there, no?
Scholars are there. MTech students are not there.
Okay.
Around 900 students are here.
Okay. So I find that you are handling the charge of Dean planning and development also. So you must be very busy.
Yeah, it's going on for last 3-4 years.
3-4 years. Okay.
Yeah.
Okay. So you do you come to Kerala or?
After the COVID, I came only once some official purpose in last
Okay.
January end.
Okay.
Otherwise, I used to come every month. for
Every
something
month.
or other. Yeah, for something or other. Yeah.
Okay. So, madam, we have around 200 registered participants. People are joining because our time given is 9:15, so maybe they'll join at the time. So, and we have representation from 23 states, and mostly it is faculty members. Around 150 plus are faculty members. Then we have research scholars and PG students. So that is the composition of the audience.
Okay.
And yeah, madam.
You are asking for 2 hours. So, okay, what do you expect?
No, it can be discussion, madam. The whole 2 hour need not be lecture. So what most of the people were, in some cases, people were taking questions in between. But in most cases, they were taking questions at the end, and that actually there were a lot of responses from the participants. So that way, half an hour discussion definitely will be required. That is my feeling from the last 2 days experience.
Okay.
So
what I'll do is I'll after 45 minutes or something like that, I'll give a break and take questions. Then,
yeah, even that is perfect. Yeah. And they normally type it in the chat box. I can, or some of us will read it for you. Either me or Ananta or someone of us will be reading it out for you, so that yeah, it'll be easier for you. Okay. So after 45 minutes, then we will break, and then after taking the questions, yeah. Fine. I think that is a good idea. So, madam, how long you have been working in this pulsed power plasma technology? I think
pulse power plasma technology, we are working from 2013, I think. 2012, yeah, 2012. Yeah.
Okay, 2012. Fine. So I find that some of the pioneering work in that area is from you, because I was searching.
It is not working in this area in the country, I think.
Yeah. Oh, okay. Shihab is also there tomorrow. One of the session is from Shihab. Yeah. So Singh, no? Ananta.
Yes, sir.
Ananta,
Sure.
I think we will it is almost 9:15, no? So we will start, let people
Start,
join.
sir.
Yes,
Yeah,
I
we
think
will
in the
start.
group also it is in the group also it is announced, no? That we have started, right? Okay.
Yes.
Okay. So welcome back. Of FDP. So today we have to start the day a very eminent speaker, Professor Ligy from IIT Madras. So she is going to talk on pulsed power plasma technology. I request Lakshmi Priya to introduce the speaker. And I request all the participants to mute their mic. There is some disturbance. Lakshmi Priya. Lakshmi Priya. Do you hear me, Lakshmi?
Yes, sir. Yes, sir.
Okay.
Sir, am I
Please.
audible?
Yes.
Thank you,
Please.
sir.
Please proceed.
Good morning, everyone. Welcome to the 7th session of the ATAL FDP on Emerging Technologies for Sustainable Environmental Management. Today, we have Dr. LigyPhilip, Professor, Department of Civil Engineering, IIT Madras, with us for the session. Dr. LigyPhilip is a Fellow of National Academy of Engineers and a Fellow of Royal Society of Chemistry. She completed a BTech in Civil Engineering from MG University, Kerala, and she did a MTech and PhD from IIT Kanpur. She has conducted quality research on treatment of industrial effluents from highly polluting industries, bioremediation of contaminated soil and groundwater, novel processes for drinking water treatment, etc. She has published more than 150 international journals and about 100 papers in conference proceedings. I wholeheartedly welcome Dr. LigyPhilip to the session. Welcome, ma'am.
Thank you very much. Can you please enable me to present the slides? Please enable me to share the slides.
Yes, ma'am. Done.
Madam, you are the presenter now.
Yeah.
Yeah, madam, it is visible, clear?
Yeah. Yeah, a very good morning to one and all. And thank you very much for the organizers to giving me this opportunity. So I will be talking about pulse power technology for the removal of emerging contaminants from water. Okay. So before getting into the topic, I'll just talk about the water scenario and why we have to focus on emerging contaminants. So as all of us know that water scarcity is a reality in the world. If you see the breakdown of total freshwater reserves, you know that only 2.5% of water, total water on Earth is available as freshwater. And in that one, around 68.7% is in glaciers, 30.1% in groundwater, and 0.8 in permafrost, and only 0.4 in surface and atmospheric water. So even if you have 2.5% fresh water, only 50% may be available for us. Okay, and when we see the water distribution, it is not in par with the population. So you can see that this is the North and Central America status. The population is around 8%, but freshwater available is only freshwater is around 15%. And when it comes to Europe, 15% of population and 8% of freshwater. And South America, you can see that the population is much less, but their water sources are much more. And Africa, in par with the population. And Australia also, population is very less, but they have significant source of water source. But when we come to Asia, when we come to the Asian continent, okay, you know that around 60% of the population is here, and we have only 36% of the population water. So definitely, the maximum water stress or water scarcity will be faced by this region. Now coming to annual freshwater withdrawal in 2013-16 data, you can see that okay, the places where okay, maximum freshwater withdrawals are happening. Okay, you can see the America around 485 billion meter cube per year, and India much higher, 761 billion meter cube per year, and okay, this is China. So these are the major countries which is contributing maximum withdrawals. And if you see the water usage, you all know that maximum water is being used for agriculture purpose. It is more than 80%. Then comes to the domestic contribute around 5 to 10%. Then industrial use, and whatever we are extracting and consuming, there is also a gap because lot of losses are happening. That's why the extraction and consumption, the difference you can see. So, and if you see the wastewater generation in India, it is around 13.87 billion meter cube per year. Okay, a large quantity of wastewater is getting generated, and okay, many agencies have stated that nearly 6 billion people will suffer from clean water scarcity by 2050. It is going to happen, and this is the data shown by NITI Aayog recently. So the population growth and the water stress index for India, major cities of India, you can see that except Calcutta, okay, much of the cities in India are having water stress issues, okay, extreme risk, okay, with respect to scarcity as well as the quality. You can see that Delhi, Indore, Bangalore, Hyderabad, Nasik, Lucknow, Chennai, all the major cities are coming in this region, and others are tending towards that one. So the future is not that great. So we have to do something with this one. And if you see the sewage generation in cities, in class 1 cities, okay, class 1 cities means population more than 1 lakh. Sewage generation is around 35,000 plus million liters per day, and the treatment capacity is only okay around 30%, less than 30% to treat the generated wastewater. Yeah, so here we can see that 32% and 68% capacity gap is there in class 1 cities. When we come to class 2 cities, the capacity for the treatment is only 8%, and 92% of the wastewater is going untreated. And class 2 cities generates around 2,696 million liters per day. And class 1 and class 2 cities together, only 30% of wastewater is getting treated, and 70% is discharged without any treatment. And you know that the wastewater is having all type of pollutants and all, so it will be a major problem. So now, okay, when we discharge untreated or partially treated wastewater, you know that lot of organic matter is there, and organic matter, biodegradable organic matter is relatively easy to degrade. But even you treat, okay, most of the treatment plants will not be taking care of the emerging contaminants like pharmaceuticals, personal care products, etc., and nutrients present in the wastewater. So when we discharge this, okay, pollutants will be remaining in the partially treated wastewater, and they are mostly persistent. So okay, they will be contaminating the water sources where it is being discharged. So you can see that, okay, so this colors, okay, this is the nutrient risk indicator to marine ecosystem, and that shows highest, and orange high, yellow medium, green low, and blue lowest. And you can see that, yeah, only Australia and some part of Africa shows blue color because the population is much less, and okay, not much is happening. But you see the regions of near India, China and all, it is completely red in color because large number of population, large quantity of wastewater is getting generated and mostly it is discharged without any treatment. And here in the Gulf region and other places, you can see that lot of orange patches. That means high levels of nutrients are there. And even South American region. Okay, so you can see that here also high nutrients. Okay, nutrients are present in the water environment. Now, another thing is, okay, so here you can see the pharmaceutical detected in waterways worldwide. And you can see that India, China, US, okay, all these countries are having much higher pharmaceutical detected in the waterways or in water sources. I think other countries are not there. Okay, mainly because okay, in African countries and all, we don't have any data available. So it is showing that okay, a light blue color. But this is a major problem, and it is distributed all across the globe. So it is not a regional problem; it is a global problem. So now, coming to the current wastewater treatment practice, if you see, what are we doing? Are you able to hear me?
Yeah, yes, madam.
Yes,
Yes.
Yeah, because somebody was telling that there is audio problem. Some message I have seen that side. Yeah, I'm sorry. Yeah. Current wastewater treatment practice. Okay, so we are generating wastewater without any control, and some places it is collected, and some places it is not getting collected, and treatment is there, and no reuse and recovery. Most of the water is getting disposed into the existing water bodies, and mostly primary treatment or secondary treatment. And we have seen that only 30% is getting even the secondary treatment. Others are not even getting that one. And many places treatment compliances are not there at all. Okay, so this is the present scenario. But okay, if you want to be sustainable, okay, this is not what we have to practice. We have to reuse and recover all the resources. Okay, but that is not happening much nowadays. Okay, so that's what I told. Okay, so we have to meet the treatment compliances and go for circular economy. So this is the only sustainable way. So when we want to reuse and recover the resources, we have to be care about the residual pollutants present in the system and their after effects and the risk posed by them and all the things. Okay, and we should have technologies to remove even the minute quantities of these emerging contaminants. Otherwise, okay, if you go for circular economy, it will create more problem than a solution in the long run. So, if you see the occurrence and distribution of pharmaceuticals and personal care products, okay, you all know that what is pharmaceuticals, the medicines whatever we are taking, okay, for various ailments, and personal care products. Okay, we use lot of personal care products like skin lotions and other things. So all those things will be finally finding its way to the wastewater. So this is the number of studies on occurrence and distribution of pharmaceutically active compounds and personal care products in different regions. Okay, this red triangle, this one shows North America, blue shows Europe, and yellow shows Asia. So in 2009-10, okay, North America and Europe were reporting many studies. Only few studies were there in Asia. And 2013-15, okay, yes, the same condition was, okay, Europe has taken, okay, much more seriously about this pharmaceuticals and personal care products. But, okay, if you see 2017 onwards, the maximum reports are coming from Asia. Okay, so a lot of people are looking into what is the concentration of these pharmaceutically active compounds and personal care products in the water bodies in Asia. And this is the details about trade and treatment technologies of PPCPs, okay, pharmaceuticals and personal care products. okay, in the different regions. Yes, initial days it was okay, dominated by North America and Europe. Then Europe took over. Europe also come up to that level, and you can see that Asian studies were very, very limited. But now, okay, most of the Asian countries are also concentrating on this one because they realize the importance of this aspects. Okay, how much problem it can create. And this is some global distribution of pharmaceuticals in wastewater treatment plants, okay, across various regions. Okay, we have a lot of data for India and even Chennai. I am not presenting that, but this is just to give an idea. This is Europe, okay, acetaminophen. Okay, you can see that the concentrations. Okay, this is that box plot. Okay, lot of concentration is okay. It is nanograms per liter, and North America, Asia, Middle East. And this is ibuprofen, naproxen, okay, salicylic acid, diclofenac, okay, okay, and many of these compounds, okay, because in Asia earlier not much these were available, so that's the reason, okay, we don't have much data, but all these pollutants are important across the world. So wastewater treatment plants, even after the treatment, lot of these compounds are coming out into the water system. So now we'll see why we have to focus on the emerging contaminants. And what are these emerging contaminants? They are the chemicals detected recently and are present in alarming concentrations. And okay, the people get, or the microorganisms get continuous exposure to these compounds. And many times we don't have enough knowledge about their fate, okay, in the environment and in human systems and all. And most of the compounds can develop antimicrobial resistance. Okay, once okay, the microbes develop resistance, they become superbug. So whatever the available antibiotics or anything will not be effective. So even a small or regular fever can become fatal because none of the available medicines will be working for this superbug. And okay, this endocrine disrupting, some of the emerging contaminants are endocrine disrupting compounds. Okay, they can cause hormone imbalances. And as I told you already, conventional treatments are ineffective in removing most of these compounds. And degradation, okay, and sometimes the microorganisms are able to degrade them to some level. So there only the biotransformation is happening. So they will be having a lot of metabolites, and many times the metabolites are more toxic than the parent compound. So this is one thing we have to be very, very careful. Any treatment technology when you adopt, we have to see that okay, the treatment system is removing all the byproducts also from the system, and the toxicity is reduced significantly. Otherwise, your treatment system will not be effective. Okay, and in India, only very limited research is being carried out, and considerable environmental health and implications are there for India. So that's why we have to concentrate on this emerging contaminants. Okay, so these are some examples. Okay, feminized male, okay, frog, okay, normal control males and feminized. Okay, this one, and you can see that deformed aquatic organisms and all the things. Okay, so these all are the problems of ECs, and definitely we have to attend the awakening call. And okay, in all over the world, presence of antibiotics in sewage is okay, reported, and the sewage can be a major source for this antibiotic resistant microorganisms and antimicrobial antimicrobial genes and all. And the interaction with bacteria in sewage treatment plant is a main consequence of development of antibiotic resistant bacteria. And NDM1 gene, okay, this is known as New Delhi metallo beta lactamase 1, okay, NDM gene, also called the superbug, discovered in Delhi and already in use. And NDM containing bacteria is resistant to a broad spectrum of antibiotic. Okay, lot uses are coming about this antimicrobial resistance, and the genes, and these genes can get transferred to other microorganisms and all the things, and it will be getting enhanced in the presence of other pollutants like heavy metals and all. So we have to be extremely careful about this emerging contaminants. Okay, otherwise it will lead to a lot of problems. Imagine you have superbug, and that superbug cause an infection for you, and none of the available antibiotic is going to work. So what will be the scenario? It will be worse than COVID. So now coming to the conventional treatment. Okay, we all know that when it comes to wastewater treatment, domestic wastewater especially, we go for primary treatment, secondary treatment, and tertiary treatment. When we wanted to recycle and reuse the wastewater, okay, we have to go for tertiary treatment, because secondary treatment will be only removing the easily biodegradable organic matter. So the most commonly used tertiary treatment technologies are filtration and adsorption, because any sewage treatment plant, okay, small scale sewage treatment plant, you can see a sand filter and a carbon adsorption system. Okay, so you know that, okay, this one will be able to remove your suspended solids and all, but okay, when it comes to emerging contaminants, it may not be that effective. Something may get removed, but it will not be giving you a complete protection. And what are the problems with this one? Efficiency against microorganism is not good, because you will be having still fecal coliforms and all, and high pressure drop, expensive, and no destruction of the pollutant, etc. These are the major problems. Then bacterial filter, biomembrane, okay, membrane, okay, purification to drinking water quality not possible. Treatment time is high, fouling of membrane. Okay, this is a big problem. So if you go for membrane filtration, okay, ultrafiltration, then nanofiltration and reverse osmosis, what will happen? You will not be able to recover more than 50-60% of the waste, the water. And what happens to the leftover water? And fouling of membrane is also a major problem, and the cost of treatment also will be very high. And another tertiary treatment we adopt is UV radiation, and you know that UV radiation will be just denaturing, deactivating the microorganisms, okay, and it is not a lasting effect. Sometimes even the microorganism will be repairing by itself and coming back. And if you have a lot of suspended solids and dissolved organic matter, UV radiation will not be effective. So control is difficult. This is another conventional method. Then we know, okay, chlorination. Okay, many times we use, because it will be able to remove many of the residual organic compounds. And many times, okay, we have to add exact doses of chlorine. But many times what they do, okay, they'll be putting fixing a dose and adding that one. So that one will be oxidizing only easily degradable organic matter. So remaining everything will be left over. And another major problem is formation of chloramines. And all of you know that these chloramines are carcinogenic compounds. Then if you add more chlorine, there will be residual chlorine effect. Okay, and if you are adding not sufficient dose, bacteria become partially resistant. And pH is also very important. You know that chlorination will be effective in acidic pH, not in alkaline pH, because when chlorine is added to water, it will be dissociating and forming HOCl and HCl, and HCl will be dissociating to form OCl minus, and OCl is not that effective compared to HCl. All these things, okay, one should know, okay, when you do the chlorination. So now people are talking about advanced oxidation process. There are various advanced oxidation processes available: heterogeneous fendon, homogeneous fendon, photofendon, photocatalysis, ozonation. Okay, in all these cases, what are we doing? Okay, we are generating hydroxyl radical. This hydroxyl radical is having much higher oxidizing capacity compared to oxygen. E naught value is 2.80. Okay, so this is much higher than oxygen. Okay, so it is able to oxidize the pollutants, and the volume of treatment time can be reduced significantly. But still, there are disadvantages. Many a times it will not be able to degrade many of the compounds, okay, which are very recalcitrant or complex in nature. So now, okay, we'll also see what are the methods adopted for treatment of pharmaceutical industrial wastewater. So they use physical treatment, biological treatment, advanced oxidation process, physical treatment, okay, coagulation, nanofiltration, reverse osmosis, adsorption, incineration, scrubbing, depending upon okay, the type of pollutants, and biological treatment. They go for activated sludge process, okay, biological aerated filter, rotating biological conductors, UASB, etc., and advanced oxidation process, Fendron process, ozonation, photocatalysis, electrochemical treatment methods. All these things are being employed in pharmaceutical industry for the treatment of wastewater. But the limitations of conventional treatment methods, as I explained, nanofiltration, narrow membrane fouling, and huge concentrate volume. So managing this one will be a big problem. And when we come to adsorption, dissolved organic compounds, surfactants, okay, etc., compete with binding sites, production of activated carbon, and another thing is here only the phase transfer is happening. Okay, so you will not be able to destruct the pollutant. Okay, you are okay, changing the phase of the pollutant, okay, from the liquid phase. Okay, you are transferring it to the solid phase, but there is again a problem to treat the strength activated carbon and the regenerate. Incineration, energy requirement, and scrubbing. Okay, we have to do costly chemicals and their safe use and disposal. So these are the problems. Okay, many places we have to use some sort of a chemical or a material. Okay, and that will be increasing the cost. Now coming to biological treatment process, temperature, organic, toxic substances. Okay, all those things will be affecting the performance of biological treatment. And chlorinated solvents are recalcitrant, and many of these PCPs are also recalcitrant. So they are not removed by the microbes. And okay, when like, multiple organic compounds are sent, okay, so there will be interaction effect. Okay, that will be affecting the removal. Then shock loss will be affecting the entire treatment system, and toxicity of the pollutants will be adversely affecting the microorganisms. And if your loading is not continuous, that also affects the process. Biological process is very, very sensitive, you all know. Now, okay, we'll see the limitations of other evaporates. Fendron process, it is widely used, but we have to supply continuously the costly chemicals, and we have to have acidic pH. And you know that in Fendron's method, lot of sludge is generated. The sludge handling is a major problem in Fendron's process. And ozonation, energy intensive, pH dependent. And this is a major drawback, low solubility of ozone in water. So whatever you are supplying, majority of ozone will be escaping, may not be utilized for the reaction. And ozone scavenging by humic substances. Okay, so they will be utilizing the ozone. So it may not be available for the degradation of pharmaceutical and personal care products. Then coming to heterogeneous photocatalyst. Okay, this alone, okay, for example, like titanium dioxide and all, it alone may not give good treatment efficiency, making it necessary to use a combination of your ozone, Fendron's reagent and all. So naturally, it will be increasing the cost. Electrochemical treatment, energy consumption, okay, that is there, but the major problem is corrosion of electrode materials, the stability of the electrode materials. As a result, okay, frequent change of electrode, and many a times the electrode will be okay, adding more toxic compounds to the treated water. So we have to be extremely careful when we talk about electrochemical treatment. And in common, many form less biodegradable and toxic byproduct, and incomplete mineralization is another big problem. Not suitable for reductive treatment of highly oxidized pollutant, because all these are advanced oxidation process. But if you take the compounds like chloroform, okay, they are in the completely oxidized form. So reductive treatment of highly oxidized pollutants are not possible. Operation is expensive owing to the usage of costly chemicals such as hydrogen peroxide, ozone, and increased energy consumption. So this is a summary of whatever is existing treatment methods. Now we'll talk about what is this power plasma. Hope most of you have heard about this technology. So here we are giving a high voltage electric discharge. Okay, so as a result, plasma is generated with physical and chemical effects. Okay, it will be having large amount of oxidizing radicals like hydroxyl radical, nascent oxygen, and molecules like H2O2, O3, and you have electrons, and you have H, you have shock wave, UV light. So you'll be getting all this, okay? So that means oxidizing radicals are there, reducing radicals are there, and you have molecules, you have shock wave, you have UV light. So you'll be having very, very reactive environment when we apply this high voltage electric discharge. And another thing is, you have to remember is no chemical addition is needed, no demand on temperature and pressure, insensitive to contaminants. Okay, so we don't have to bother about the organic loading rate or any of those things. Okay, and whether if the loading is not continuous, also your system is not going to affect. Can be used for treatment of contaminated water, air, soil. So, okay, streamers in liquid phase. Okay, so you apply this high electric discharge, you'll be getting this type of streamers. Okay, that one will be generating all this radicals and molecules and waves. Okay, so that is what is happening in pulse power plasma. Fine. So here, what we are doing, high voltage pulse corona streamer discharge. What we do, we will be having lot of energy. We are storing it and sudden release. So when we do a sudden release, okay, you know that lot of energy is there. Okay, imagine a dam is there with lot of water and we open it instantaneously. What will happen? Lot of energy. Or how are we kicking a football? Okay, you kick the ball and at a stretch give a lot of energy. So like that, that is what is happening in high voltage pulse corona streamer discharge. So chemical process induced in water. So what are the things happening? Formation of ozone and its dissolution in water. So this is the electron. Okay, you'll be having a bottom plate here and high voltage is applied. So the streamers are coming. So as I explained, you'll be having electrons. Okay, ozone, OH, H2O2, O3. How it is forming? Okay, ozone. Okay, O plus. Okay, so this one will be giving you O3. Okay, formation of hydroxyl radical. O3 plus OH minus give you O3. Okay, so these are the chemical reactions I have given, and some amount of water vaporization will be happening, and this water will be reacting to form hydroxyl radicals and all. Okay, lot of reactions are going on in the system, and you'll be getting all type of reactive compounds. Okay, and so you have dissociation, you have vibrational or rotational excitation. Dissociation, water plus electron. Okay, you can get OH, H dot and E. Ionization, you get 2 electrons and H2O plus, and H2O plus H2O gives you OH and H3O plus. And here vibrational rotational excitement, you will be getting E, H plus, OH, O, all these compounds will be, or radicals will be generated and provide high removal efficiencies of a large variety of contaminants within a short contact time. So you know that all these things are highly reactive. So as a result, you will be getting high removal efficiencies of a large variety of contaminants within a short contact time. And for plasma can be thermal or non-thermal. Okay, and types. Okay, you can generate the plasma in the liquid phase. Okay, you see the electrodes are here. Okay, one electrode and this one the thing. So the plasma is getting generated in the water phase. This is gas phase. Okay, this is the ground electrode and the other one. Okay, so here the plasma is getting generated. And hybrid. Okay, you can see some amount is in the liquid and some in the gas. So depending upon your requirement and nature of the pollutant, you can adopt any of these things. So I'll give a summary of this plasma technology. Okay, plasma, energetic electrons, excited species, free radicals, ions, molecules, and photons. All these things we are getting, you have seen reactions, and produced by the ionization of gas by high voltage electric discharge. And this initial series of chemical and physical reactions and effects. And reactive species, okay, I already mentioned, okay, all these species are generated. So you can have oxidation, you can have reduction. So highly oxidized compounds and highly reduced compounds can be treated by this method. Am I audible? No?
Yeah,
Yes,
madam,
madam. Yes, madam.
audible, but at times, there is that oscillation. I mean, some sort of disturbance.
Yeah. So maybe the net problem I won't be
Yeah,
able to
yeah,
do.
yeah. Yeah.
Yeah, because I am seeing some message that's I asked. Yeah. Okay, so when we talk about the plasma technology, it is a combination of various advanced oxidation process. We have seen various advanced oxidation process. But when we talk about pulse power technology, we can consider it as a combination of all these IOPs, or it will be having the effect of all these advanced oxidation processes, because you get all the species, whatever is usually present in advanced oxidation process, and you also get some reducing species. And I told you non-thermal and thermal, and we are working on non-thermal methods. And these are the ways OH radicals are generated: dissociation of water, ionization, vibrational, and OH is also formed ozone and oxygen atom. Okay, so you get large quantity of ozone and OH radical apart from all other radicals. And advantages: operation at atmospheric condition. You don't have to increase the temperature or pressure. And this is very, very important. When we talk about other treatment technologies, we talk in hours and days. These are in minutes. Okay, very rapid treatment, superior degradation efficiency, no requirement of chemicals, environment friendly technology, medium energy consumption. These are the advantages. So, hope you got some idea about pulse power plasma. Now we will get into how it is working and all. So this was our first reactor. You can see that these are the electrodes, and we have a aluminium this one electrode in the bottom. So you can see the streamers are forming here. Okay, here the streamers are forming in the air. Okay, water is below that one. So what are the things here? You have OH radicals, H plus, O, O2, HO2, H2O2, O3, UV, high electric field, intense wave. And if you see the oxidation potential, hydroxyl radical 2.8, or nascent oxygen 2.42, ozone 2.07, H2O2 1.78, and oxygen is around 1.42 or something like that. Okay, so everything is having very high oxidation potential. Okay, so naturally it is an advanced oxidation process, and I also told you it is capable of reducing the compounds also. So first I will talk about okay, how we started the initial things, okay, because nobody was aware of this one. So we just started in 2013. So first person worked in this area with me was Dr. Raj Kamal. So initially we have to understand all the mechanisms and all. So we reactor setup, optimization of electrical and physicochemical parameters, quantification and kinetic study. Okay, then we have carried out batch study to understand. Then mechanism of degradation, toxicity. Then we have gone to continuous study. So this is what first we have done, and after that one, what all the things we have done, I'll explain during the course of time. So this is a circuit diagram for the reactor setup. Okay, so you have a transformer, oscilloscope. Okay, people may be thinking that okay, 23 kilowatt and not so much of energy. But please remember that this is generated only for nanoseconds or microseconds. So the total energy used for the treatment will be very, very little. Okay, because the generator, though we want high voltage, the type use, the type we need is very, very less. So the total energy consumption will not be that high. So this is the setup. So when we started first, okay, we had a water bath and all because it was a batch system. So temperature was rising. So we were adjusting the temperature by providing a water bath and all. So this was the very primitive, okay, our reactor setup. We have gone a long way. I'll tell you what we have done. And voltage and current characteristics, okay, we have taken the help of electrical engineering faculty because I don't know anything about this voltage, current characteristics and all. So Professor Saradi was helping us to make this one. Different voltages. Okay, what is the pulse? Okay, see the time. Okay, 4 into 10 raised to minus 6 seconds. That means the microseconds. Okay, we are getting in 1. Okay, 0 to 1 microsecond maximum pulse was coming. Okay, this is pulse current. Okay, again it is in microseconds. Okay, so that's what I told you. The total energy consumption will be very less because the pulses are okay generated in 4 microseconds. So okay, if you want to go for any treatment process and adopt that one for treatment, first thing we have to do is quantification. We have to do the kinetics of the system. So if you want to do, a proper understanding, if you want to have a proper understanding of the system, okay, we have to quantify these components. How much is the reactive species generated in the system? So that is very, very essential. So first one we have done is the quantification of ROS. So initially we were not knowing how to quantify all the things, so we had to develop the methods and all. So hydrogen peroxide, okay, the reaction with NL ion, okay, we have followed. So okay, that is the method we have followed. Ozone, okay, and then dimethyl DPD method we followed. OS radical, hydrazone, okay, this reaction. Okay, and dictated by HPLC UV visible, and superoxide radical, nitro blue, tetrasodium chloride method we have used for the quantification of superoxide radical. Okay, so this is trend of ROS formation. You can see that you have ozone, not too much high concentration, and hydroxyl radical. You can see that concentration is keep on increasing with respect to time. And this is superoxide radical, and hydrogen peroxide, you can see that it is increasing, and after that one it is reducing and becoming stationary. So what is happening? You've seen the reaction. H2O2, okay, combining H2O2 dissociate and form hydroxyl radical. So that is why, with respect to time, okay, this H2O2 concentration is decreasing and hydroxyl radical concentration is increasing. You see the reaction here. OS radical plus H2O2 gives you H2O2 or this one HO2, and H2O2 gives you hydroxyl radical. Okay, so this reaction is going on. So that's why after some time, H2O2 concentration is reducing. But you know that compared to H2O2, hydroxyl radical is much more effective. So if you want to take the system, okay, to the field, we wanted to know, okay, how the system will be functioning with respect to various conditions. Because in the real water system, you know that there are various ions, and okay, also, okay, we should know how the voltage, frequency, etc., is affecting the performance of the system. So we have looked into different initial voltages, and you can see that we can see that as the voltage increases, the concentration also increases. Okay, and here 17 has given least and 23 has given maximum. Similarly, frequency also, have the frequency more the concentration, and pH, okay, acidic pH was favoring, because you know that carbonate and all, okay, will be scavenging the hydroxyl radicals. So higher the pH, lower the generation of hydroxyl radical. Then similarly, alkalinity, the alkalinity, there was slight reduction in the formation of hydroxyl radical, and organic content. Okay, because if organic content is there, whatever the hydroxyl radical generator will be utilized by that one. So that's why you can see reduction. Yeah. This is for, okay, similarly, we have looked for hydrogen peroxide formation also. Okay, it was showing the same trend, but you can see that after some time, okay, the concentration is decreasing. I told you what is the reason. Okay, so here, okay, alkalinity, humic acid, glucose, all those things we have looked into. So similarly, we have looked into for other parameters also. Now I'll get into the degradation studies. So emerging contaminants degradation using pulse power things. So what are the things we looked into? Okay, so how it is happening, what is the kinetics, and what is the degradation pathway, whether mineralization is happening, okay, whether okay, the toxicity is getting removed. So all those things we have looked into. I'll show you a few examples, because we have looked into many emerging contaminants and their degradation using pulse power plasma technology. So pesticide. Okay, you know that pesticide is also coming under emerging contaminants. So initial concentration, we have first selected carbofuran, because we have selected pesticides from various groups, and a concentration of 1 milligram per liter was used. Okay, and these are the voltages, 15 to 25 kV voltage I have used, and this shows the yield. Yield means how many grams of the pollutant is degraded kilowatt hour. So that is the yield. You can see that, okay, the time you see 1 milligram per liter is getting degraded 100%, okay, within 6 minutes. Any other technology, if you want to, okay, use, okay, the degradation time will be, okay, 3 hours, 6 hours, like that, isn't it? So here, everything happened in a very short period of time. So voltage, as we expected, higher the voltage, better the performance, you can see. And this is frequency effect. Again, the same thing. Higher the frequency, better the effect. Again, you are getting complete removal in a short period of time. Then we have looked into the degradation pathway. So we could see that, okay, so this is the pathway. It is okay, OS radical is attacking, and you are getting everything. And finally, OS ring cleavage, and it is going to carbon dioxide and water. Okay, so this is second pathway, OS radical. Then, okay, it is going to a reductive pathway. Okay, then you will be getting, okay, this compound. Okay, and this is the fourth. Okay, this is again a reductive pathway. We were the first ones to report this reductive pathway for the carbofuran degradation. Okay, so that's what I told you. It is not only an advanced oxidation process. Okay, reductive degradation is also possible by pulse power plasma technology, and you can see that in all the things, really you are getting carbon dioxide and water. So the mineralization is happening in the system. And how can we assess the mineralization? Okay, okay? So we thought that we look into the ecotoxicity assay. So we have used microalgae, Chlorella vulgaris. Okay, so when we put the water to the water bodies, okay, whether it is going to create any pollutant. Okay, so this is percentage viability versus the control. Okay, so you can see that initially, okay, first, okay, when the treatment started, okay, you could see that it is coming down. The reason is you have, okay, what we have done is at 0 time we have taken the sample, okay, then okay, after 2 minutes of treatment we have taken the sample, after 4 minutes, 6 minutes, 8 minutes, 10 minutes, and the viability test was conducted 24 hours, 48 hours, and 72 hours. So you can see that after 2 minutes of treatment, the toxicity was increased. The reason is many metabolites will be generated as soon as you give the pulse power. So that metabolites, some of them are more toxic than the parent compound. That's why the toxicity is increasing here. Then you can see that with respect to time, all those metabolites are getting removed and your toxicity is reducing. And after okay, around 10 minutes, okay, there is no toxicity. Okay, after 10 minutes of treatment, there is no toxicity left over in the system. And this is the TOC removal in the system. You can see that the TOC also is getting removed almost completely. So this shows that the system is not only degrading, okay, it is completely mineralizing it and removing the toxicity also from the system. So this is needed when we wanted to tell that your technology is working well. So once we completed that one, okay, we have gone for 2,4-D, the pesticide degradation, and here percentage degradation under different pH we have looked into, and we also looked into, okay, in the real wastewater you'll be having nitrate, sulfate, chloride, carbonate, chemicals, etc. How the effect is, okay, when these ions are present in the system. So you can see that yes, there is slight, okay, effect. Okay, so because no ions, okay, you are getting 100% removal in 4 minutes or something like that. When the ions are present, okay, the rate is slightly reduced. Okay, but you can see that within 10 minutes, 8 to 10 minutes, complete degradation is happening. So what we felt is, okay, even in the real water sample, you will be able to achieve complete treatment. Maybe the time may be, okay, slightly increased. The treatment time may be slightly increased. So we could see that here also everything is getting degraded. We have done all the pathway analysis and all the things. Okay, if you want this one, we have large number of publications, okay, related to pulse power technology. You can see, okay, those things. I'm not going into the details of all. So now, okay, so that is about pesticides. Now we thought that we'll look into pharmaceutically active compounds because that is the major concern nowadays. So this is diclofenac. We have looked into 3 different pharmaceutically active compounds: diclofenac, carbamazepine, and ciprofloxacin. Okay, and all the 3 combined together. Okay, so you can see here also we have looked into the voltage and different frequency, and you can see that yes, voltage is having an effect, but everything is getting removed. Okay, here also we use 1 milligram per liter concentration. Similarly, diclofenac also. Okay, so you can see that within 2 minutes, more than 90% removal efficiency is happening. Where else we'll get this type of a treatment efficiency? And ciprofloxacin, okay, it is slightly, okay, it was taking slightly longer time compared to other things, but still, okay, we were able to degrade everything. So depending upon the complexity of the compound and the chemical nature of the thing, the time needed may be slightly increased, but any compound, irrespective of the system, okay, the pulse power technology is able to degrade that one. Here, okay, the thing diclofenac, okay, the PK KOW value is 4.51, carbamazepine 2.45, and ciprofloxacin 0.28. So whether anybody can tell why diclofenac is getting degraded faster? Because I told you, okay, here we are using the pulse corona discharge in the air phase. So if you have high KOW value, this is highly hydrophobic. So these compounds will be mostly concentrating on the surface of the water. So when the pulse discharge comes, the compounds will be getting attacked faster compared to a hydrophilic substance. Hydrophilic substance, it will be highly soluble. It will be in the bulk liquid. Okay, major concentration will be present in the bulk liquid. So when you go for air streaming, okay, hydrophobic compounds will be degraded faster. But if you are doing the streaming in water, hydrophilic compounds will be degrading faster. So that's why the compound nature will be affecting the degradation. So then we have looked into LCMS analysis. Okay, this is the blank, and before treatment diclofenac, you can see that very high. Okay, and we could see a peak. Then after 4 minutes of treatment, you see that the peak is disappeared. That means it is completely gone. Similarly, carbamazepine before treatment, after 4 minutes. Okay, so ciprofloxacin before treatment and after treatment. So everything is getting degraded. And we also looked into the effect of pH and radical scavengers on the degradation and the rate of reactions, etc. So here, this is pH 5, how the carbamazepine degradation. Okay, you can see that time of complete degradation. Okay, DCF took around 4 minutes. Carbamazepine took around 6 minutes at pH 5. Okay, pH 7. Okay, diclofenac at the same time, but ciprofloxacin, the time is increased slightly. Okay, as pH increase, the time is increasing, but you are getting complete degradation. And this is in presence of alkalinity. Okay, 200, 400. Okay, when alkalinity is high, your treatment time will be slightly increased. And this one, okay, we are humic acid. If organic compounds or other organic compounds are present in the system, how it is getting degraded. And you can see that, yes, it is having some effect, but everything is getting completely degraded. And this is this yellow, this blue line shows the rate constant per minute. So you can see that DCF is having a very high rate constant compared to ciprofloxacin, and I told you the reason. And the rate constant is slightly decreasing as the pH is increasing, as the alkalinity is increasing, as the humic acid concentration is increasing. But significant. What I am trying to tell is, this very clearly shows that at field condition, the technology will be working because all the adverse conditions we have tried. And this is the yield. Okay, what is the gram per kilowatt hour? You can see that as other concentration increases, the power requirement will be increasing because you have to for longer period. So naturally, the power input will be increasing. Okay, so that is what we have done. Somebody is asking a question. I will stop now, or maybe under 2-3 slides.
Maybe after 2-3 slides is fine, ma'am.
Yeah, so because I'll just complete this one so that it will get a clear idea. Yeah.
Yes.
Then we have one for single and mixed pollutant degradation. So, so here the concentration effect you can see 1 milligram. When you increase the concentration 4 milligram, time is increased. Concentration 10 milligram. Okay, time is further increased, but you are getting 100% degradation. And this is mixed condition. Okay, 1 milligram. Okay, mixed condition, you can see that time is slightly increased compared to single pollutant condition, but everything is getting degraded. Okay, you can see. Okay, it is. And the rate constant also, compared to single pollutant or mixed pollutant, the rate constant is slightly decreasing. This blue lines you can see is in the blue points. Okay, but everything is, only thing is, your yield will be slightly changing based upon the condition. But still you are getting high degradation efficiency. Then, for everything, Okay, we have looked into the ecotoxicity the same way. So this is 0 minute. You have very high concentration, 2 minutes, 4 minutes, and by 6 minutes treatment, the toxicity is decreased. And this is for mixed condition. This is for ciprofloxacin. Okay, for 24 hours, 48 hours, and 72 hours. Okay, the same type of a thing we have looked into for pharmaceutically active compounds also. And we also did this diffusion set test. Okay, this is another method to assess the toxicity. So you pour the treated water in a membrane, okay, and put it in the dish, and you can see the zone of influence. So this is without any treatment. You can see that 25 mm is getting affected. 2 minutes, zone of influence is reduced. 4 minutes and 6 minutes, you cannot. Okay, you are not seeing any influence on the toxicity effect is not visible at all. Okay, is it clear? Okay, we are this is a membrane, small membranes. Okay, there we are putting 1 microliter of the treated solution and put it in the Petri dish. So wherever toxicity effect is there, you can see that there is no bacterial concentration. Okay, here you can see that 25 mm is the influential point. Okay, that means that much of zone of incubation. After 2 minutes of treatment, it is reducing. After 4 minutes and 6 minutes, there is no zone of incubation appear. So that means the toxicity is getting reduced significantly. Okay, so then we have gone for continuous flow reactor. Okay, very small system. Okay, just to see whether we'll be able to. Okay, very primitive way of treatment. So this is the spacing need. Okay, this is our bottom plate, continuous flow. You can see all the needles here. Okay, so this is the, and you can see the pulse power, pulse. Okay, this blue color you can see, isn't it? Where the plasma is generated. Okay, and okay, we have distilled water, lake water, river water, everything we have looked into. Okay, the degradation of diclofenac, carbamazepine, carbofuran, 2,4-D, ciprofloxacin. Definitely, distilled water, you have much higher K value. Lake water, it was slightly less. Raw water. Okay, so what I am trying to tell is, yes, everywhere it will work, but you need little more time. Okay, for getting 100% removal efficiency. Okay, so I'll stop here and I'll take questions for now. Then afterwards I'll continue the remaining thing. Yes.
Yeah, madam, I'll read out some of the questions that are already there in the chat box.
Yes.
So one is the plasma technology cost effective when it is implemented in the real-time treatment plans? So that was.
It is cost effective. I have a table I'll show you. Okay, compared to other advanced oxidation processes. Okay, which is used for treating this type of compounds. For example, pharmaceuticals, personal care products, etc. So compared to other advanced oxidation processes and all, okay, this is cost effective. Okay, so there is no problem. Only cost is the power cost, and we have calculated the cost based upon our batch system. Now we have a pilot scale system. So we could see that the cost is coming down significantly. Okay, because as the volume increases, the per unit cost is coming down significantly.
Okay. Then the next question is not on pulse plasma, but then is there any analytical method to quantify the sulfide radicals?
Yes, I will be talking about that one towards the end of my talk.
Okay.
Because we have looked into that one in detail. I'll show you.
Okay.
There is no direct method. We have to do it indirectly.
Okay. Then, madam, I have a few questions.
Yes.
Now, this pulse, each pulse was actually in microseconds.
Yeah.
But then, at what interval will you be applying this pulse? It has to be intermittently applied, right? Or rather, this pulse has to be there continuously, right?
See, we will be giving the voltage continuously, but this pulse will come, one spark will come, then there will be a gap, then the next pulse will be coming. Okay, the gap will be much. Yeah, the gap will be at least 100 times more than the pulse time.
Okay, so that means
Okay.
still in seconds, or
Yeah.
maybe instead of microseconds, now it is milliseconds, right?
Yeah, milliseconds or seconds. Okay, I'll tell you. Okay, this one come, then okay. I'm sorry. Okay, it will be in between gap. Okay, you'll be having 5 to 10 seconds gap. It will not
Okay.
continuous streaming. It will come.
Okay.
Okay, just like lightning, it will come, then stop, then next one will come like that.
Okay. So that means even though the treatment is, we may have to adjust the flow in a continuous reactor. We may have to adjust the flow based on. Because I find that the treatment is happening, even though the pulse is only for a few microseconds, the treatment is happening in 4 minutes or, see
what is happening is it will be continuously coming, isn't it? Okay, one pulse will come, then after 5 seconds or 10 seconds, next pulse will come. So when one pulse comes, okay, you'll be having lot of these radicals generated. So
yes.
that radical has to diffuse into the water and it will be getting reacted. Okay. So and we could see that if you stop in between 2 minutes without even giving any power, that was increasing the efficiency, because you'll be having too much of radicals. So everything may not be getting completely utilized. So I'll come to that one. This is the basic thing we have done to understand. So now we have many other reactors.
Okay. Then what will be the effect, or what will be the case when ions are present, say maybe sodium chloride, which are charged? So will that?
So that's why I have shown you, isn't it? Chloride ion, sulfate ion, nitrate ion, all those things affect. Okay. So it has some effect. Okay, but it didn't have too much of effect. And towards the end, when we were using actual wastewater, we have done with actual wastewater lot of studies. So we could see that if sulfate and chloride is present, it enhances the treatment.
Oh, it enhances the treatment. Okay.
Yeah, because sulfate will be generating sulfate ions, sulfate radicals, and chloride will be generating chlorine and ClO. Okay, so that one will be enhancing the treatment. Not all the compounds, certain compounds which can be affected by these radicals.
And will that result in the heating up of the system, presence of these ions?
If you go for a batch system and you continuously do the pulse power, the temperature will come up. That's what I told you. In our initial system, we had a water jacket.
Okay. Yeah.
In this system, we have a water jacket. But when we go for continuous system, the water is continuously flowing. So and it is not getting stored there for a long time. So no heat increase is there. Maybe a few degrees, some 2 or 3, maximum 5 degrees centigrade. That's all.
And will the presence of ions have any additive effect on the temperature, something like that?
We didn't see much distilled water and other things. We didn't see any. And I didn't. Nobody asked me that question. But here in this batch system, we were having one problem, because the plasma is happening in the liquid, the gas phase. So the nitrogen present in the air was getting oxidized to nitrate. So the nitrate concentration in the treated water was very, very high.
Okay.
So that was one of the major problem we have faced. Then we have rectified that one in our further reactor designs and all.
Okay. Madam. So that was from my end. Now, if some of you want to unmute and ask, you're free to do that. Like, you can do that, or you can even type in the chat box. So from the participant side, any more questions? So they are asking, what about heavy metals?
See, this is advanced oxidation or reduction process of heavy metal as such. Nothing will happen. But we could see that. I'll show when we were treating the real wastewater. We could see that there is some sort of a coagulation happening in the system. When suspended particles are. So as a result, much of the other pollutants are getting removed. So that is an indirect effect. Because these ions are getting generated in the system. So that one will be neutralizing, the charge neutralization of the particle will be happening, and little bit of electrode material will be dissociating. So that also will be enhancing a sort of a coagulation. So as a result of that one, okay, your turbidity, organic matter, and some amount of metal concentration get reduced. It is not because of oxidation or reduction. It is because of other physicochemical processes happening in the system.
Okay, madam, like you might have tried in low COD water, no? Not.
No, that's why I have shown you, isn't it? Okay, we have put humic acid as well as glucose, okay, to find out the effect. Okay, and we have taken real pharmaceutical wastewater and did the studies. I'll show you in the next half.
Okay, okay. So the BOD or COD of the wastewater was like 400, 500 like that, or?
Yeah.
Okay.
Only thing is, okay, see, if it is easily biodegradable, I will not advise you to go for.
Yeah, definitely. That is why. That is
Okay.
what.
It will not be economical. Okay, so whatever you can remove by biological, you remove and use this as a test treatment.
Advanced treatment.
Yeah.
Yes.
Any more questions?
Okay.
Hope my
So
voice is clear now.
Yeah, yes, madam. In between, actually, that some, as
Yeah,
it was
because our
fluctuating.
institute, some because everybody will be doing the things
Yeah,
simultaneously.
right. So, okay, madam, I think there are no further questions in the chat box, so maybe we'll continue. Huh?
Yeah. So my time is up to 11:15, isn't it? I'll stop at
11.
11.
Yeah, yes.
Because there is something else is there. Some other question came down.
Yeah, there is one question. Yeah, which is best? Just a second, madam. I'll read it. Which is best suitable for drinking water? Maybe normal. Which is best suitable drinking water? Normal hand pump water, Bisleri water, then Kangen water, RO water. I don't know what is that Kangen water. Japan technology.
See, okay, RO water will be having very low TDS value, total dissolved solids. So the water will be corrosive in nature. Corrosive means with respect to the solubility or soluble ions present in the water. So if you drink that type of a water, it is not that healthy. So I feel if after RO, if you mineralize the water and drink it, that will be the best water. Okay, so the TDS level in the range of 200, 300 is always good, and up to 2000 is permissible. So it's all depending upon other parameters. It is not only the TDS which make the water potable or not. You have to test other quality and see whether your water is potable or not. Is it fine?
Okay, so I think now, yeah.
Okay.
So we will assume that, yeah.
Okay. So I'll go ahead. So now, okay, so until now we were talking about pharmaceuticals and personal care products and pesticides. So we thought that whether this technology can be used as a single technology as a tertiary treatment. So then we have to look into the disinfection efficiency of the system also. So this is the thing. Okay, before treatment, you can see that so many bacteria were present, and after treatment, everything is removed. I'll show you. We use E. coli, tryptone and platon method was used for the treatment. The effect of different this one, so we have used a bacterial concentration of around 10⁻⁶. The reason why we have used such a high concentration is everything was getting killed in no time, so we were not able to measure when we were using low concentrations. And this is what I was telling you. Okay, so here you can see that this is 10 minutes we continuously given the pulse. This is 5 minutes. Okay, we have given. Okay, and then 2 minutes gap. Then again 5 minutes. Okay, this is 2, then 1 minute gap, 2, like that we have given for 10 minutes total. You can see that if you give 2 minutes pulse, then give a gap, okay, that was much more effective than continuous giving. Because continuous giving, okay, this is interesting. Why I'm telling is continuous giving, okay, lot of radicals will be generated and they themselves will be reacting and many will be getting nullified. So you will not be getting complete effect. So if you give a gap, 2 minutes, then 1 minute gap, again 2 minutes pulse, 1 minute gap. So within short period, you will be getting much more efficiency. So 10⁻⁶, okay, bacterial concentration has come down to 0 in 6 minutes time. Because if you go for any other disinfection method, okay, it will take much more time. Okay, and effect of voltage and all also the same. High voltage, better efficiency, frequency, high frequency, better efficiency. Then as other system parameter, pH, alkalinity, chemic substance, glucose, stability, all those things. Okay, we have looked into. So, okay, when the stability increased, okay, you can see that, okay, the time needed for the complete reduction. Okay, see this one, okay, 0 minute, okay, 2 minutes, 4 minutes, 6 minutes, 8 minutes, okay. So, okay, within 6 minutes, everything is reduced. Okay, the stability increased, the time is increased. Similarly, humic substance has other ions are present or other compounds are present. Your treatment time will be increasing slightly, but you will be getting 100% removal even for this system. Then another thing, okay, we have looked into is, okay, in UV radiation and all, you know that if you keep the water for 24 hours many times, the bacteria may reappear because, okay, some deformation will be happening. They'll be able to repair it and, okay, again, can become active. But in here, okay, you can see that, okay, it was complete destruction of the, okay, cell is happening. So this is the inactive cells. Then initially the micropores were developed. You can see, isn't it, the pores in the cell. Then cytoplasm oozing out. You could see these all are 10 images at different time periods we have taken. Then, okay, after this is oozed out, all the cells were clumping together. Okay. I have wrinkled appearance we could see, and total cell wreckage was happening. So this shows very clearly that complete microbial cells were destructed. It will never come back. So that is what we could see. And we also looked at the LDF, okay, same release into the system. How with respect to time, the enzymes were, okay, protein, okay, release from the cells, okay, 2 minutes, 4 minutes, 6 minutes, 8 minutes. Okay, so you can see here, and this is protein concentration from cells and protein concentration in cell-free supernatant. Okay, you can see how it is. Okay, from the cell, protein concentration came down. That means it was oozing out, and the cell-free supernatant, that concentration is increased. Okay, and DNA degradation study also you can see. Okay, you can see 0 minute the bands, linear plasmid and circular plasmid you can see, and this is the chlorosomal DNA. 2 minutes itself. Okay, you can see that it is getting disturbed. Okay, all the three. By 4 minutes, everything has gone. Okay, so DNA complete cell destruction is happening. That's all. So this is the total cost. Okay, we have calculated. Okay, so this is based upon the batch system. Okay, around total capital cost is around 87.28 per year. Okay, you don't treatment cost is coming around 9,384 per meter cube. Yes, it is a very high cost. Okay, because we calculated this one based upon that batch system. So this is what we have compared the cost of cost of different advanced oxidation systems. Okay, this is dollars per meter cube. You can see that carbamazepine, phenol, TCE, pharmaceuticals. Okay, in the present study, you can see that the cost is coming around 34 and 138, and it is comparable with other treatment systems. Somebody was asking me this question, so that's why I thought that I'll tell you. Okay, then conclusion, I don't want to read everything, different ROS, okay, then combined effect we have looked into and all. Okay, so this one you have seen, but yes, we have faced a lot of challenges. Selection of reactor configuration for easy degradation, because I told you many of the reactive species were escaping from the system. The mass transfer was not happening, so not even 20% of the species was utilized for the degradation. And electrode material erosion and rust was a big problem. Scaling up of the reactor in continuous mode, maintaining uniform distance between electrode and water was a problem. efficiency was not in accordance with the design of batch reactor, and nitrate generation and pH dropping in the treated solution was another problem. So these were the challenges. So then we decided to take care of each of these challenges. Okay, so that is what I am going to talk about. So we are able to see my this one screen.
Yes, madam. Yes, yes, it is clear.
Okay.
We can.
Okay, so first what we have done is we have gone for sequential flow plasma reactor. Okay, because I told you much of the reactive species were just staying there, and mass transfer was a major problem. What we did is we thought that instead of keeping the water stationary there, it may be better to spray the water into the electrode. You can see here, isn't it? So the water was pumped from the reactor, and we were spraying into the reactor this region, so that whatever the thing coming, the contact will be much better because it will be in fine bubbles. So the surface area is much more, so the diffusion of the reactive species will be much better. So sequential flow plasma reactor. Earlier we were getting a nitrate concentration of around 230 milligram per liter and all. In sequential flow for plasma reactor, the nitrate concentration also reduced significantly because the plasma is not there continuously in the air, and nitrogen is not getting reacted because you have other reactive species available here. So much of the plasma is used to treat the pollutant rather than generating nitrogen. So this is the way nitrate is created in the system. Okay, so and hydroxyl radical is getting generated. So by recirculating the water and reducing the mass transfer, we could reduce the nitrate formation and we increase the efficiency significantly. You see, so 1 milligram, 2 milligram, 5 milligram, 10 milligram, we were getting very high removal efficiency. This is verapamil, a very difficult to degrade compound. Hence mass transfer suitable for high concentration, reduction in nitrate formation by 80%. And another thing is no water jacket was required because we are sprinkling the water, so heat is getting dissipated, so there was no problem of heat generation. This was first thing we have done. How to reduce the nitrate formation in the system. Then so how the percentage degradation we were getting this one flow rate. We tried different flow rates. Contact time 4 minutes, 10 minutes, and 12 minutes, and yield also increased significantly in the system. When we went for the recycling, earlier the yield was yield was 1 or something like that. Here the yield was much higher than the batch system. Then after seeing this sequential batch reactor, we went for continuous plasma reactor. So you can see here. So this is the plasma generator. You can see the plasma will be getting generated here. So this is one electrode. This is another electrode. And this is our water spraying system. Water is just getting sprayed in the region where the plasma is getting generated, and the water is getting recycled until the pollutant is continuously completely degraded. And you can see that the continuous degradation of the pollutant. So you are getting 15 minutes complete degradation of all these compounds. And you can see that the flow rate 33 ml to 133 ml we looked into, and we were getting high TOC removal also, and yield also is increased. And you see here the nitrate concentration has come down to 8.6 milligram per liter, and you know that the drinking water standard is 45 milligram per liter. So in this type of a reactor, the nitrate concentration is taken care, and the efficiency also increased, and there is no water jacket required, and high yield. Yes,
Madam, just a second. Madam, are you showing the slide number 65 or you have changed from there?
I have changed from there.
But I don't know, is it the same? For me, it is still 65. Others?
Same, sir. Same here.
What I'll do is I'll stop and I'll share again.
Yeah, please.
I go to 65, you have seen. Okay, so this is 66. And now it is changing, isn't it?
Now it is moving. Now it is moving. Yes.
Yeah,
Yes.
so here what I was telling is contact time for, okay, you are getting 98.6% DCF degradation, okay, and 12, okay, so 10, okay, this is different concentrations. This is 1.1 and 2 milligram per liter, 5 milligram, 10 milligram, okay. So what I am trying to tell is in the continuous system, you are getting a better efficiency and yield. And after the sequential batch reactor, we went for a continuous reactor. So this is the continuous reactor. I told you the plasma is getting generated here. This blue color shows the electrodes, and this orange color shows the water jet, water is coming. So where the plasma is getting generated, there we are sprinkling the water. As a result, we got very high removal efficiency. Even TOC removal is 99%. Yield is very high, and nitrate generation is reduced significantly. Okay, we were getting only 8.6 milligram per liter, and nitrate permissible limit is 45 milligram per liter. Okay, and here tungsten electrode and copper ground we have used. No recirculation. Water jacket is not needed. High yield, we got it. Okay, so how the pH for pH, then we have done all other studies in continuous system. How the different pH, alkalinity, humic substances, glucose, all those things getting affected, and you can see that everywhere you are getting significantly high removal efficiency. Okay, so this also different flow rates or hydraulic retention time is the degradation and yield. Okay, you can see that as the contact time is more, your degradation efficiency is more as expected. And this is for 4 milligram and 10 milligram, because 1 milligram what was happening is within no time it was getting degraded, so we were not able to measure anything. So that's why we went for a high concentration, and this is the yield. Yield, definitely yield will be reducing when the flow rate is less, because up to certain level the degradation will be very fast. Okay, and you all know that the concentration gradient plays a significant role. So if you want to come to that 100% degradation, naturally, towards the end, your yield will be slightly reducing, but you are getting significant yield here also. So these compounds also we were able to degrade completely. Okay, and here you can see that yield was increased more than 2 times. In the continuous system. Okay, then continuous system also we looked whether complete degradation is happening and all, and we could see that everything is happening. And here also we did the toxicity study. Okay, because we cannot tell that by analyzing the parent compound whether the things will be getting degraded and toxicities. Okay, there you can see here. This is the zone of inhibition. Okay, so here it is reduced, and here nothing is there. Zone of inhibition. Okay, this is for 10 milligram, and this is for, yeah. Okay, and now I was showing little bit more, but after at that time, 10 minutes, we were not having any toxicity. So this is the cost analysis here. Operation cost is coming per meter cube. Pencil for continuous flow reactor. Okay, so this is $0.67 per meter cube. Okay, what I told you earlier, whatever the cost I have shown is very high, because we are keeping very little volume, 50 ml, and for long periods. So that's why we were getting a high cost. This is a continuous system, so the cost is significantly reduced. Okay, so this is batch reactor studies. Okay, everywhere whatever I can discuss, it is summarized here. Now, based upon that one, we have made the pilot scale reactor. You can see, these all are the plasma reactor, because we have taken the photo in the evening time so that the plasma can be seen very clearly. Okay, this is a 1 meter cube. Okay, 1 meter cube for 8 hours. Okay, 1 meter cube per day reactor. Okay, so you can see that for the pulse created, and we are spraying the water here, and within 6 minutes HRT we are giving all the residual pollutants from the secondary treated water is getting removed. Okay, so this is working in our STP now. Okay, so now I'll talk a little bit quickly, under 15 minutes, about pharmaceutical wastewater treatment using pulse power plasma technology. Now we were taking the treated water where low concentrations are present, how it is effective. But when we go to the pharmaceutical wastewater, not only pharmaceuticals, other VOCs are also present. We were looking into chloroform, chlorobenzene, toluene, MIBK, and methyl isobutyl. MIBK means methyl isobutyl ketone, and their mixtures, how it will be able to degrade, because these are major compounds present. The pharmaceuticals will be very, very low concentration present in pharmaceutical wastewater. So this is chloroform degradation in liquid and gas phases, because chloroform, chlorobenzene, all these things are volatile organic compounds. When you take one in the gas, the liquid phase, it will be partitioning with the gas phase, so some concentration will be always there in the gas phase also. So just measuring the liquid phase analysis will not be telling you whether everything is degraded. So this is the degradation in aqueous and gaseous phase. Blue line shows the liquid phase and red color shows the aqueous phase, the gas phase. And this is different concentrations, how it is getting degraded. And this is the yield. Complete liquid phase in 10 minutes, we were able to remove TOC removal around 91%. Percentage removal increase with initial concentration. Energy efficiency was around 0.652 grams per kilowatt hour. Okay, so then we looked into effect of pH, conductivity, alkalinity, etc. You can see that yes, it is having some effect. Okay, and higher CF removal at alkaline. So here, you can see that usually we expect a removal high in low pH, but here we were getting high removal at higher pH. So CF removal increased with conductivity and alkalinity. So the reason CF, you all know that it is a completely oxidized state compound. Carbon is CCl4. Okay, so it is in the completely oxidized form. So the reductive reaction is happening here. That is the reason why the electrons are responsible for the removal. So that's why the CF removal increase with increase in pH. Then effect of reactive species, scavengers and dechlorination. So we have looked into nitrate. Okay, we use isopropanol as oxygen hydroxyl radical scavenger, because we wanted to know whether it is hydroxyl radical which is doing the degradation, or is it the electron which is doing the degradation. So you can see that. Okay, so we have used one molar isopropanol as the OH scavenger, and then we have used nitrate. Nitrate is an electron scavenger. Okay, so you can see that when hydroxyl radical is scavenged, you are getting a better removal, but when nitrate is put in the system, nitrate is put in the system, the degradation reduced. That means the electrons are playing a significant role in the system. And we also looked into the dechlorination, because if chloroform degrades, chlorine will be coming into the system, and we could see that chlorine. Okay, the stoichiometrically we have seen 97.5% of dechlorination has occurred in the system. Then the proposed pathway. Okay, here you can see different pathway. Everywhere it is getting converted to carbon dioxide, water, or carbon dioxide and chloride. Okay, different pathways we have proposed. Okay, so somewhere hydroxyl radical getting involved. Okay, so somewhere all those things, somewhere it is reductive degradation. Okay, so all those things are, and we are getting this type of a intermediate also. And byproducts and intermediates during the degradation. This is the chloride concentration. Okay, and you can see that acetate and formate, these are very low molecular weight organic compounds. They were accumulating in the system little bit. They are not very toxic, but they were not easily degradable. It was taking time for the degradation. That's why the TOC removal was 97.5%. Remaining was caused by this acetate and formate. And nitrobenzene and 1-chloro-3 nitrobenzene, all the other toxic compounds, you can see that with respect to time, concentrations were coming down. Okay, and toluene, naphthalene, benzene, 1,2-dichloro. All those things are formed, but with respect to time, everything has come out. Okay, then comparison of plasma degradation of chloroform, chlorobenzene, toluene, and MLBK. Complete degradation, 16 pH at which highest degradation is happened. Major reactive species. Okay, the chloroform, it is electrons. Okay, toluene, both electrons and hydroxyl radical. Okay, MLBK also both. Okay, TO3 mole, all those things we looked into. Then, okay, we have looked into the mixture. Okay, in the mixture, percentage degradation. Okay, MLBK was slightly complete the liquid degradation of CB and toluene. Okay, and MLBK took more time. It is highly soluble. That is the reason. And gas phase, okay, we could get complete degradation. Then the effect of various electrolytes, organics, and turbidity on degradation efficiency. Because if you go for a real wastewater, all these things will be coming. That is the thing. So this is carbonate, phosphate, sulfate, chloride, nitrate. You can see here, if sulfate is present in the system, your degradation is much better. Okay, then okay, chloride. Okay, chloride also enhances the degradation. I am comparing it with the distilled water. So chloride, sulfate, and even nitrate. Nitrate also enhance the degradation because they will be coming the corresponding radicals. Sulfate, chloride, and nitrate enhance CB removal. Okay, so how? Okay, so you'll be getting the Cl. Okay, then HOCl, all those things, and sulfate will give you sulfate radical. Nitrate will give you nitrate radical. So these are the things. Okay, that is the reason why there was an enhancement in the removal efficiency, and the oxidation potential of sulfate radical is 2.5 to 3.1. Okay, whereas hydroxyl radical is 2.8. Half-life for sulfate radical, okay, is 30 to 40 microseconds compared to OH radical 1 microsecond. So this is more stable. So sulfate radical is more prone to react with OH, NH2, electrons from aromatic compounds compared to OH radical. And formation of sulfate radical in small system. So okay, somebody was asking me how to find out the sulfate radical. So direct measurement is not possible. So we have done indirect measurement. So isopropane alcohol is a good scavenger for both OH radical and sulfate radical. Okay, whereas TBA react around 70 times faster with OH radical than sulfate. So you do with IPA and TBA, then find out the difference, then you will be able to get the sulfate radical concentration. Okay, so CB in the so you can see that CB in this one isopropyl alcohol, the degradation was less, but okay, TBA you can see that it is almost equal to the distilled water. That means sulfate radicals were more effective compared to hydroxyl radical. Indirectly only we will be able to do that one. Then effect of sulfate on OH radical concentration. Okay, different sulfate concentration we have done it. Okay, if sulfate concentration increases, OH radical concentration was decreasing in the system. Okay, then we have looked into effect of COD on the degradation. Okay, so we have added some 5,000 and 10,000 milligram per liter COD. Okay, glucose. That means COD is slightly higher than that because the pharmaceutical wastewater and all will be having very, very high COD. But still, we could see that okay, the VOCs are getting removed. The reason is VOCs are more hydrophobic at that one. Okay, it was getting, and the electron is responsible for the removal of chloroform. That's why chloroform was not removal of chloroform was not getting affected by the COD. But other compounds, there was a reduction. And effect of turbidity on VOC removal, because your industrial wastewater will be having turbidity also or suspended solids. So we were looking into a turbidity, and you can see that 750 and 200 NDU. Okay, the turbidity CF and CB removal. This is the chloroform and chlorobenzene, and you can see that as the turbidity increase, slight increase in removal efficiency in the case of CB. The reason is you can see that some flocks are forming and it is settling down. Okay, so something is getting absorbed on that one and getting removed. Okay, the plasma, okay, minimal effective turbidity, majority of the plasma-based reactions at gas-liquid interface. E formed at the water surface and bulk in solution. Plasma removed turbidity by flocculating the colloids. Okay, now continuous plasma degradation. We have a continuous reactor. So, okay, 800 ml per minute. Okay, same type of a reactor we have used, but okay, recirculated in a faster rate. Complete degradation of chloroform, chlorobenzene, toluene at a HRT of 33.3 minutes. MIBK removal was only 70 point. I told you, okay, it is highly soluble, so it was difficult to remove. And the nitrate concentration was only 18.8 milligram, though we have given a detention time of 33.3 minutes. Detention time means total time the water will be getting into the reactor. So that's the way we have calculated. Okay, so VOC mixture also we have looked into, and the mixture also we were getting very good removal except MIBK. And we also looked into effect of initial concentration of VOC, because we know that lot of radicals are getting generated. But, okay, so there will not be any effect on the loading initially. Only when the loading is more than whatever the radicals getting generated in the system, then only the degradation efficiency will be getting affected. So this region we call it as diffusion limited region. So initial time, okay, it is not the radical which is the rate limiting one. It is the diffusion of the radical into the liquid is the rate limiting step, and this is reaction limiting zone. Okay, that means radicals are the rate limiting step. Okay, so this one we have done for okay 100%. This is a 100% removal line. Okay, so diffusion limitation region and reactive species limitation region we have done. Okay, in DLR, ROS faced diffusion limitation. In RLR, ROS was sufficient. Okay, so energy consumption of continuous reactor. This is for chloroform and chlorobenzene. As the timing, okay, energy consumption. Okay, this is okay percentage degradation and energy consumption. If you want only 80% or 80 to 90% degradation, energy consumption is very, very less. But if you want 100%, naturally the energy consumption will be increasing. I told you concentration gradient and concentration available. And okay, so here the energy consumption is much lower than the batch system. The major reason is spraying of wastewater increased the interfacial area of contact and facilitated enhanced mass transfer of ROS for the treatment. And the electricity cost per meter cube is coming around $1.85 per meter cube for actual pharmaceutical wastewater treatment. Okay, it's not that high. Okay, so then this is for actual pharmaceutical wastewater. This is the concentration of various pollutants. So what we have done is, okay, initially we tried with coagulation, flocculation, then go for plasma treatment. Okay, plasma with coagulation and pre-treatment. Okay, so the COD removal we were getting around 99%, BOD removal. Okay, and BOD COD ratio was remaining almost same. And change in concentrations of VOC. See, you can see that VOC concentration is so high, 1,200. Acetone, isopropanol, methanol, DCM, toluene, IPCA, concentrations have come down significantly after 60 minutes of plasma treatment. Okay, and initially we did with coagulation, flocculation, but then we thought that why should we go for that one? Whether we can go for direct treatment and see how it is getting removed. Okay, so change in BOD, COD, you can see that you are getting complete removal in 140 minutes BOD and COD. Okay, and with coagulation and flocculation, acetone 73%, direct plasma you are getting 67, IPA 74, 69, methanol 80, 72, DCM 78, 74, toluene 92, 88. This one 97, 96. What we are trying to tell is, without coagulation also, the real wastewater treatment was happening with the direct plasma. The reason is coagulation is happening during the plasma itself. Continuous treatment. Okay, so finally, okay, we adjusted the HRT up to 150, and you are getting 100% degradation, and 91.8% COD and 150 minutes. This is the conclusion. Complete liquid phase degradation. Okay, all those things we have listened. Yes, thank you very much. Now we have 15 minutes for question answer.
Yeah, yes. Okay, thank you, madam. So shall I read out some of the questions in the chat box? This was actually a continuation of earlier question on RO. Is it good to use RO systems in house?
RO systems in the house, okay, if your water really needs that type of a treatment, if your water source, first you get it tested, okay, then you see what are the pollutants present. If no pollutants are present, only TDS is there, even TDS up to 500, 800, there is no harm in drinking that water. In such cases, don't go for RO. But if you feel that there may be some contaminant like heavy metals and all, then you go for RO, but RO with mineralization. There should be a mineralization step present in, because just RO water will not be having the enough TDS, so that water will not be good for health. So nowadays, there are ROs coming with green RO. So after the reverse osmosis, the water goes through a filter, which is having calcium carbonate and other things. So the dissolved solids concentration in the treated water will be increasing. That will be good.
Okay, madam. Then I'll just read out what is written here. More than 50% population in USA is taking groundwater, but here in India, pollutants are heavily present. So how do you recommend the use of groundwater over RO system?
In the US, many people are using groundwater. In India also, many places groundwater is safe. I am not telling that everywhere groundwater is safe. So the RO becomes so popular because of the vendors and the industry people. They wanted to sell the RO because you know that whatever the RO available now, the recovery is only 30 to 40%. So 1 liter of water you are getting, 1 liter of water you treat, only 400 ml you get, or 300 to 400, remaining 600 to 700 ml you are wasting. So yes, some places the water is contaminated. In such places you have to go. So don't blindly go for RO, because any municipality, when they supply the water, they have to meet the drinking water standard. Without that one, they cannot supply the water. So most of the time, that water is safe, free from many of the toxic chemicals and all. Maybe some turbidity will be present, some bacteria may be present during the distribution. In such cases, you can go for a microfilter and a UV. So that will be enough. But in some places, if you feel that there is contamination, then you go for RO, but don't directly drink the RO water because your TDS will be less than 40. So you mineralize and drink it. Hope I cleared your doubt.
Okay, so can I read out the next one?
Yes.
How can we treat the river water as it is a bigger system to work in comparison to any wastewater treatment systems? Is it practically possible to treat rivers against emerging contaminants?
Yes, see, it is not the river which is the source of emerging contaminant. The pollutant which is going to the river, which is the source. So what we have to do is, and I told you the major source of emerging contaminant is wastewater, because when we consume some pharmaceutical or personal care product, only 20 to 40% is getting absorbed in our body. Remaining, 60 to 80% is getting discharged through feces and urine. And personal care products, everything will come out when you take bath and clean yourself. So all these things will be finding its way to the wastewater treatment plant. So if you treat your wastewater properly, these emerging contaminants will not be getting into the river system. So that's why we are telling that, yes, we have to treat the wastewater properly and see that these pollutants are not present in the wastewater. But if you are discharging the wastewater without any treatment and you are using the river water for drinking purpose, okay, you have to take care of these contaminants at that time, in the water treatment time. So, okay, apart from the conventional treatment, you may have to go for adsorption or any of these methods. Okay, and if you feel that your water is highly contaminated, then you go for RO. But after that one, you mineralize it.
Okay. Okay, madam. Then another question: will plasma technology will it be a better option for the treatment of oil and grease?
Oil and grease. Okay, why should we go for plasma technology? Because oil and grease, it is very easy to separate it from the liquid. So in such cases, instead of we are spending so much of energy and degrading it, you separate it. Phase separation will be the best method for oil and grease. Okay, and if any residual is present still, because you know that flotation or any of those things, you go completely, it will not be getting removed. So in such cases, some residues are present, definitely your plasma technology will be removing that one. But I won't advise PPT for oil and grease treatment, because when we can treat it with a less costly technology, why should we go for a high energy intensive method?
Okay, madam. Then Kavita Kulkarni is asking, what is the cost of continuous reactor setup?
See, whatever we have made, all these things are single units. So the cost will be very, very high. When we make multiple units, the cost will be coming down. See here, the cost is only, you have to make that electrode, one plate and one needle type electrode. So that is the only cost coming. All other things are the tank and the pipes. So in that way, the cost will not be very high. Only thing is the pulse power plasma generator. That cost will be around, whatever we are using now, because it is a highly sophisticated one, it costs around 20 to 25 lakhs. Okay. Other than that, the reactor cost is very, very minimal. Okay, you have a tank and you have 2 electrodes. That's all.
Okay, madam. Then Akansha is asking, this technique is pH dependent. Some pollutants are effectively removed at low pH, some at high pH. If we want to reuse it, we need to adjust the pH. Also, yield cost is high. Then how will you convince the industry people to go for this technique?
So that's what I was precisely telling you. Okay, though you get optimum removal at that pH, you don't have to go to that pH. Okay, I have shown you from pH 3 to pH 12. So pH 7 also you are getting very good removal. Okay, but compared to pH 7, pH 12 is working better for some pollutant and pH 3 is working better for other pollutants. So you don't have to adjust the pH or change anything. Work at 7. Only thing is, instead of 6 minutes, it may be going up to 10 minutes. That's all. Okay, the rate constant will be slightly lower. So if the rate constant is slightly lower, you can give slightly more reaction time. And here we are talking the reaction time about only in minutes. So it doesn't matter, truly speaking.
Okay, madam. Then Varsha Parmar is asking, what is left in water after reverse osmosis?
Reverse osmosis, after reverse osmosis, if the reverse osmosis system is working very well, nothing will be left over. Okay, some monovalent ions will be left over. That's all. Little bit, very little.
Okay. Then can we use plasma technology for tannery effluent? So that was from Jnana Prakash.
See, tannery effluent also, I'll suggest you first go for the primary treatment and biological treatment and all. And after that one, whatever is there, very difficult to remove. Okay, organics, because all are not biodegradable. If you want to remove that type of a thing, then you can go for this one, pulse power technology. But in tannery wastewater, most of the COD and BOD will be able to remove by conventional biological treatment, followed by just ozonation or chlorination. So these are for very, very complex organic molecules. Okay, so you understand the molecules, and which is not possible by conventional methods, then only we go for advanced oxidation, because compared to the conventional method, this will be more costly.
Okay. Then, Madam Anjali Gopakumar is asking, ma'am, can we use plasma technology for treating estrogen-derived personal care products?
Any organic compounds, okay, can be degraded by this one. Okay, however complex it is, okay, we'll be able to remove it.
Okay.
That's why I have shown a wide range of, starting from pharmaceuticals to personal care products to all those things I have shown. And we have much more data with many other compounds also. I didn't put everything. So any organic compound, either it is highly oxidized or highly reduced or intermittent, we'll be able to remove it.
Okay. Then, Madam, I have a few more questions. In the continuous batch reactor, or even the other also, will stirring have some will that result in some improved efficiency, stirring or some sort of mixing? Because after all, any
the batch system, the stirring will have some effect, but still, okay, compared to that one, okay, we could say we have tried stirring, but compared to stirring, we were getting much more efficiency when we were spraying, because in the spraying you are getting very fine water molecule, water droplet, and the plasma is getting generated there, and you see there are lot of reactive species are there. So if you have much more surface area, the diffusion will be much better. So stirring, you will not be getting that type of a surface area. Okay. So that's the reason why we went for this spraying type reactor.
But then stirring may result in that nitrogen oxide formation, no? Because there can be air also coming.
See, here what is happening is, when you are spraying it, water is available, okay, and in the water, okay, all the reactive species will be immediately getting reacted with the organic compounds present in the droplet.
Okay.
So as a result, not much radical is available to react with nitrogen and producing nitrate and all. Okay. So that is the reason why spraying is reducing the nitrate formation compared to other one.
Okay.
The faster we utilize the reactive species, the better the reaction and lower the nitrate generation.
Okay. Then have you worked on soil with this technology, madam?
We have not. I have not worked. Okay, but people because only 2 or 3 groups are working. Okay, there is a strong group in US. They are looking little bit. Okay, we have looked into water and air. Okay, and for industrial thing.
Okay, and in the case of air, then the problem of oxides of nitrogen formation will be still high, no? Or do we have some method to
see? Air. Air pollution. Okay, because it doesn't have to diffuse into the water system. Okay. It will not be there. Because here the problem is we have to give much more time, because whatever the species generated in the air has to diffuse to the water. There the problem comes. Okay, in the air phase it will be much faster.
Okay. And then there was an upper voltage that you used. Was it what limited that? Could you go for a higher voltage?
Our system. Because
yes.
Okay, because we can go maximum only up to 30. Okay, without instrument order, because it is only for research purpose we bought it, isn't it? So.
Okay. So then there are a few more questions in the chat box. Can plasma technology be beneficial for dairy effluent? So I think
dairy effluent is highly biodegradable, isn't it? It will work. Okay, I have shown you, isn't it? 1,000 and 10,000 this one and all BOD reduction is there, but dairy effluent is so easily biodegradable. Why should we go? Okay, always remember, biological process is always sustainable compared to any other process. Okay, when it is not possible to treat with biological, then you go for these things. Blindly don't take any technology.
Yeah. Then I have a few more in the chat box. Then from Reena Tomar, I'll read it. Yeah. Can I read that?
Yes.
Someone was asking something. Anyway, I'll give it to you after reading out this. So, what method of treatment is suitable for rural areas, as both economy as well as quality as a concern? Like I have just slightly modified her question, but then probably this is what I meant.
See, a rural area, Okay, I want to suggest this method, okay, because who will take care of this one, okay, energy, and okay, you know that, okay, some knowledge and knowledgeable person should be there for operation. So we have developed some technologies for rural areas also. If emerging contaminants are there, photocatalysis, okay, which is working with sunlight, solar powered or solar exciting photocatalysis. So that those type of technologies are available. There are a lot of other technologies available. Okay, so you look into if it is a centralized system in rural area where you wanted to give the water and all, you'll be able to use this one. Otherwise, I will not recommend this one. So you can go for many other easy systems.
Okay, then those who are asking, they can now take over. Like someone was asking directly. Yeah, please. You may unmute and then ask.
Morning, madam. This is Lakshmi Narayanan.
Yeah.
Could solar desalination be one method by which we will be able to provide water, purified water with a sustainable solution, because it can cater its own?
Yes, okay, there are many plants. Okay, people are putting up, isn't it? Solar plants, okay, for desalination and all. In Chennai, it is there, and even in the Lecture7 and all, they have put it. Okay, some places they are using even the ocean thermal difference. Okay, for making the desalinated water. Okay, wherever the solar energy is available and the sea is nearby, okay, it is sustainable, because in Chennai from IIT Madras itself, many some faculty members have put up plans, okay, with the support from DST.
Okay, actually, I am from Chennai.
Yeah.
As part of a project from the college, I am working on a solar desalination plant at a place near Mahabalipuram. That's where my college is located. But
Yeah.
it is not actually for removal of salt only from seawater, but also from groundwater. See, when I look at some villages nearby my institution, I find that the water has a lot of contaminated salts and other things. So, they all depend on the water cans that is being distributed, which is people pay every day. But we could see very clearly in some villages they are still fetching water only from wells directly by walking for now. So I was looking for a solution by establishing a solar desalination plant. I am actually remodeling the collector area with a different design and trying to come up with more purification or more desalination in a single particular area of absorption.
Okay.
So my question is, will this be a feasible solution?
Yes,
because
okay.
I'm on the project.
Okay, our from our institute, okay, Professor Sundararajan, T. Sundararajan, and okay, Reddy from mechanical engineering. They all are working and they have installed many units there in the Mahabalipuram area.
Do you belong to IIT Madras?
Eh? What?
Are you from IIT Madras?
I am from IIT Madras.
Okay, fine. Ma'am, I could just share your email ID so that I'll be able to communicate
You
with
can
people.
get their contact address directly from the directory, T. Sundararajan from mechanical engineering.
Fine, madam. Because I already have contact with professors like Kamarajan sir and other people. B.S. Murthy, Dr. Kamaraj, and with medical department mostly I have contact. So Professor Sundararajan, right?
Yeah, mechanical engineering.
I'm a mechanical engineering by nature. Thank you very much. Thanks for your explanation, madam.
So any more questions? We are at 11:18 now. Ananta?
Sir, we will end up maybe. Yeah, there is no more questions. I felt from
there are no. There is just one question. Yeah. Plasma technology is better than enzymatic treatment for removal of antibiotics from wastewater. Like, it's a question. Is plasma technology better than enzymatic treatment for?
See, any biological treatment system, you know that, okay, you may get 80%, 70%, okay, efficiency. But if you want to remove completely, the biological system will take lot of time. Okay. And another thing is, okay, these concentrations will be keep on changing. Okay. And very low concentration, you may not be able to, okay, use biological process. That is the limitation. So in such cases, okay, this type of advanced oxidation methods will be better.
Okay. So I think we will end now because we need to start the next session in another 15 minutes. So thank you, madam. Thank you, madam, for the excellent session. And there was a lot of discussion. So on behalf of the Department of Civil Engineering, on behalf of my institute, on behalf of the organizing committee, and on behalf of the participants, I extend a very warm thanks to you, madam, for this excellent session.
Thank you very much.
Yep.
And thank you for the patience that all of you had for 2 hours. Okay.
Thank
Okay.
you, madam.
Thank you very much.
Thank you, madam.
Thank you.
Okay. Bye-bye.
Bye.
Thank you. Thank you.
So participants, if you want, you can take a break. The next section will start exactly at 11:30. Okay. Thank you. Sir.
Yeah. So I think
our
next
expert.
you can tell about. I think many are asking about the poll. Maybe you can tell the alternate arrangement. I think there are people who are still not clear about that.
Today there is no poll. Maybe at least for this session there is no poll. We will be taking it directly from WebEx. Based on your presence, it will be giving directly how long you are there in that particular portal. Accordingly, we will be taking attendance. As instructed yesterday, if you are available in the portal at least for 60 to 80% of the time, then only it will be marking you as present. Otherwise, it will be marking you as absent. Okay. So preferably we may not be conducting polls, and some cases we may. That depends. So there is no conformity on it. Thank you.
Okay, Ananda. So I think now we will maybe wait for the next session to start. Maybe in between, you may load the next presentation slide. In the sense, the slide on the next expert. Maybe.
Yes. Abhinaya or Lakshmi, just wait. Let us have a trial, and then you can go for the looping slide. Okay. I'm just making our expert as the presenter now. Nima sir. Nima sir.
Yes, I'm there. Yeah.
Sir, actually, you can once you can share and we can have a trial. Now you are the presenter.
I'm fine. Hello.
Yeah, it's visible, but in grid form.
No.
It's not in presentation mode.
Okay, just check.
Yeah.
Is it in presentation now?
Yes, sir. Now it is in presentation.
Okay.
Yeah. Yes, sir. Yes. We could see the first slide.
Okay, right. Thank you. So,
Sir, actually, we are taking the presenter's privilege for some time, maybe for another 5 minutes. And after introducing you, we will be giving the privilege again.
Okay, absolutely, no problem.
Okay. Thank you, sir. Thank you.
Thank you.
Lakshmi. Yeah. Sir, one clarification. We can have the questions in between or at the last.
If some important those things somebody has, they can ask in between also.
Okay, sir.
But sometimes it disturbs the flow.
Okay, maybe sir, actually you can take as per your wish, and then we will have the question session.
Okay, yeah, fine.
Okay, sir. Lakshmi, shall we start?
Yes.
Yes.
Yes, sir. So, welcome back to the 8th section of our FDP, or second section of the third day. I hope you people are enjoying the FDP. And today we have Dr. Sudhir Kumar Nima, Scientific Officer, H, from Institute for Plasma Research, Gujarat, who is having 18 plus years of experience in the field of plasma and its relevant technologies for different applications. Sir will be talking about solid waste management using environment-friendly thermal plasma technologies. And I welcome you, sir. I may ask Lakshmi to introduce our expert.
Thank you.
Lakshmi?
You will too?
Yeah.
Thank you, sir. Welcome at the 8th session of the FDP. We have Dr. Sudhir Kumar Nema, Scientific Officer H, Atmospheric Plasma Division, Institute of Plasma Research, Gujarat, with us. Dr. Nema done his PhD in polymers and allied field and is working as a Scientific Officer H at Institute for Plasma Research since 1993 on plasma processing and plasma chemistry. Presently, he is heading Atmospheric Plasma Division at IPF. In his leadership, several plasma-based technologies have been developed and transferred to industries. His major contributions are in the development of technologies, mainly plasma pyrolysis technology for the safe disposal of medical waste and plastic waste, plasma gasification for energy recovery from waste, surface modification of Angora wool to enhance cohesion among fibers, plasma activated water using plasma jet, demonstrating using plasma air jet environment-friendly plasma technology to achieve optimum rubber to glass bonding, glass-like coating on metals and alloys using non-thermal upon plasma technologies for textile and apparel, published by Woodhead Publisher India, is covered by. His contributions are visible in the form of several Indian patents and papers in peer-reviewed journals. The Gujarat Council of Science and Technology, Government of Gujarat, conferred him Dr. Vikram Sarabhai Award for the year 2002-2003 in the field of environment for the work of the National Academy of Sciences conferred NASI Reliance Industries Platinum Award 2000 for innovation physics. Dr. That's it. Welcome.
Hello.
Yes, sir. Sir, you can share.
Yeah. Is it I have shared?
No, sir. Actually, it is not visible. We could see your folder, sir, not the presentation. Sir, maybe you can leave once and join again.
Okay.
Sir, you are the presenter now.
But
No, sir. Audio is fine. Sir, you can open the PPT.
Yeah, that I have opened. Already it is there.
Yeah, it's fine now, sir.
Okay.
Yeah.
So you are seeing on the full screen.
Yeah. Full screen, first slide.
Okay. Hello.
Yes, sir. You are audible also.
Yes. Fine. Thank you very much. I sincerely thank the organizing committee for particularly Dr. Ananta Singh for giving me this opportunity to speak on solid waste management using environment-friendly thermal plasma technology. And I particularly in this program, faculty development program on emerging technologies for sustainable environmental management. And as you are seeing the topic solid waste management using environment-friendly thermal plasma technology. It is having three topics: solid waste and its management, and environment friendliness, and then the thermal plasma technologies. So a lot of things you are going to learn in the next about one and a half hour time. So basically, I am from Institute for Plasma Research. This is located at Gandhinagar here, and this institute is under Department of Atomic Energy, where we are main focus of the institute is on fusion research, where small atoms they like helium and tritium, and they can be fused, and large amount of energy from fusion you can generate. So institute is working on different plasma based systems where you can generate high temperature plasma, and the sun, you see the sun where the fusion is going on, and continuously you are getting large amount of energy. So similarly, the tokamaks are also known as artificial sun on the earth. So they are being developed in the world, and Institute for Plasma Research is one nodal agency this ITER program. This is International Thermonuclear Experimental Reactor, which is being developed at Cadreche, France. So Institute is participating and key representative because from India, and 7 countries in the world, they are working together to demonstrate the break-even point, to demonstrate the experiment where the amount of energy is given to the system, and we are generating much more than X amount of energy through fusion reactor. So a lot of work is going on at the institute, and different tokamaks are there. Aditya is the first tokamak which the institute has developed, and then SST, steady state tokamak, second tokamak, where understanding the plasma physics part that is going on. And in 1997, this facilitation center, this has come out from the institute. Basically, this was to promote commercial exploitation of plasma technologies and how we can help our Indian industries as well as we can help the society. So that was the main motto. And this facilitation center, which is about 25 kilometers away from this institute in Gandhinagar, it is working as a link between institute as well as industries. And we are developing from very conceptual stage. We start developing the technology, and afterwards we develop the prototype systems, do the incubation, and then finally transferring the technologies to industries for its use. So here we are going to discuss what we are going to discuss in the next 1.5 hours. That is there. Like we are going to discuss on solid waste generation and different type of solid waste that is generated in India, plasma, the most active state of matter. We are going to briefly talk, I'll be talking on that. And in conventional way of waste disposal and management, and in thermal plasma, then ideal technology for waste disposal and its management. And development at whatever development work that has taken place on these thermal plasma technologies at Institute for Plasma Research. On that I'll be talking. Afterwards we'll discuss on the wealth from waste and energy recovery from waste, and finally we'll summarize. So are you seeing the slides? When I'm changing the slides, you are seeing the next slide?
Yeah, yes, sir. Now the waste slide is there with picture.
Yeah, right. Okay. So basically, we are having large variety of waste we are generating in our country. This is also the scene in the world also. Plastic waste, plastic bottles, and a lot of plastic pouches. You can see here the tire waste and the solid waste which is generated, electronic waste, and so there are large variety of waste what we are generating, and typically one person generates half kg 500 grams of waste on an average. So India is producing more than 1.4 lakhs tons of waste, MSW, municipal solid waste, only. More than 1.4 lakhs tons of municipal solid waste. This was about 4 to 5 years before. Now this quantity is going to be much more. Plastic content in the waste MSW is typically 10 to 20%, because many of the rack pickers, they also collect the plastic, and they sell it for recycling. There is the debris and various other kind of things used to be there in the waste. Lot of moisture and the bio